In our last video lecture, we talked about combining or creating ensembles of models. And in this class, we talk about a special kind of modeling, which is known as hierarchical or multi-level modeling, that has application to specific types of important problems. So I'll first talk about hierarchical models, how you build them, and then we will turn to an example of their use using data from radon testing. So Bayesian multi-level models are generalizations of regression models where parameters vary by group. As we know, in Bayesian regression, we treat the parameters as random, and that's no different for multi-level models. We're treating them as random here as well. Hierarchical models are a special case of multi-level models where the groups are nested. And multi-level models really allow us to answer a variety of questions about group data, where there are varying sizes to groups and other conditions that change between groups that mean that we really want to look at group relationships to the response variable. Some examples of this are schools and students or teacher scores. So consider student scores. We might be interested in knowing whether student scores change based upon the school that the student is in, and whether that changes, the schools change based on the districts that they're in, the school districts that they're in. So we'd have a multi-level model or a hierarchical model in this case because they're organized hierarchically from the district to the schools to the students. Another example would be hospitals and patients. We'd be interested in maybe the outcome for patients varying by hospitals, and the hospitals in turn varying by the geographic district that they're in. Once you see this idea, you can quickly see that we can apply it to lots of problems. Economic or social outcomes, for example, varying by geographic or political units, by which county you're in, which state you're in, which country you're in. These kind of things are all interesting questions that we want to look at, and hierarchical models, and more generally multi-level models, give us a way to do this. So let's set up the problem structure for hierarchical models. And it's basically the same structure that we have for all regression problems. We start with n observations of a target or response variable, call it yi, where I is 1 through n, the number of observations, and we have some number of predictors, say k, and that gives us a data matrix n by k. We'll let xi be the ith row of this data matrix. Now, the difference is we're going to suppose we have j groups, and these groups are indexed by some index variable little j. Now, the traditional approach to this problem is to model it with dummy variables, and since we have j groups, we'd have j minus 1 dummy variables, and we'll let them be z1 through zj minus 1. So our regression equation then looks as shown. We'd have yi is equal to alpha plus the matrix multiplication of theta times xi plus the dummy variables plus the error. Now this dummy variable approach works in the sense that it creates new intercepts for each of the groups that we're looking at, but unfortunately it creates an artificial comparison because everything is really compared against the one group that we've left out. And it also adds these dummy variables, which without thinking about the conversion of the dummy variable to the intercept makes it very difficult to interpret. So there are other approaches that people use, and we'll talk about those, and then we'll talk about the hierarchical approach, which is the one that really is more effective for this problem. So the first approach that people propose is a complete pooling approach, and this just basically ignores the groups. So we put all the data that we have, regardless of group, in a one data matrix, and we use that as our way to represent the response. So this is one approach called the complete pooling approach. Just ignore the groups and put all the data together. The opposite approach to the complete pooling approach is the no pooling approach, which basically creates one equation for each group. So now instead of having one big regression equation with all the data ignoring the groups, which is the complete pooling model, the no pooling model says every group has their own equation. And that's what we show here. So the y sub j, for instance, represents group J, observation I. The alpha j I represents the intercept for group J, observation I, and so forth through the rest of the equation. So these represent one equation for each of the J groups. Now this has the advantage that we are very specific about the groups. We're absolutely modeling their impact upon the response. The disadvantage is that in many real problems we have groups that have varying sizes, and some groups are relatively small and other groups are relatively large. This will make the estimates for the small groups very unstable, and small changes in new observations can cause a tremendous change in the regression equation that we got. So there's yet another approach, and the other approach is called the partial pooling approach. The approach here, though, basically creates intercepts, and it doesn't use any predictors. So we're showing the alpha hat j. This is the intercept for group J. So it's saying, okay, this is what I estimate on average things will be like for the response in group J. And the way that we get that is we formulate it with a number of variance computations. So we let sigma squared y be the within group variance computed using either an average or a value for each group. So in other words, we can either use the average of the within group variances, or we can use the specific within group variance for that group in order to help estimate its intercept. Okay, and sigma squared alpha is the variance of the average values within the group. So this is shown as y bar j. So that's the average value of the target or response variable within the group. And y bar all is the overall average of the response variable or target variable. Averages from groups with less observations in this approach are going to carry less weight, and that's called shrinking. It's shrinking towards the overall average. So they're moving away from what they would be if we just computed them for their group with just the observations in their group, and they're moving toward the overall average, and that's called shrinking. And this is what we want in general. We would like these groups that don't have many members, because their regression equations are going to be unstable, to be a little closer to the overall average for all observations, because that will provide greater stability to the estimate. Averages from bigger groups are going to carry more weight, and as a result, they'll be closer to the unpooled estimates, the estimates that we would get if we were just to look at them as their own group and do a regression based upon that group. All right, so the basic hierarchical model has varying intercepts and varying slopes. So we can allow both the intercepts and the slope to change with a group. So notice this is different from what we just saw with this partial pooling approach, which only allowed for intercepts. Now we're going to allow for a combination of intercepts and slopes to be representative of the group. And the notation here shows the alpha ji, where alpha ji is the intercept for that group J, and theta ji are the parameters for that group J. So, and I, of course, is associated with the observation. It's the individual observation. So what's changed in this regression equation then is that that notion of having each one of those parameters be associated with its group. But notice that unlike what we had, and we had a similar notation when we were doing the unpooled models where we developed a regression equation for each group. What's changed here, though, is notice that the yi isn't by group. And what we've done is we've done this for all observations. So we're not looking just at a regression equation for that group. We're looking at all observations in this data set to build a model. So to summarize then, complete pooling can't provide estimates for groups. It's just a way of bringing all the data together and ignoring groups entirely. So it doesn't give us a sense of what's really happening in our problem space where we're interested, for instance, in knowing if a school is responsible or contributory towards a student's performance, or if a hospital is contributory, specific hospital contributory toward a patient's outcome. No pooling, on the other hand, gives poor and possibly extreme estimates for groups of small sizes. Another way to say it is they're less stable. So the smaller the size of the group, the number of observations in that group, the less stable those results are going to be. And the question is, can we do better than that? And the answer is yes, we can build strength by using the full data set, and that's what we do with the hierarchical models. Partial pooling does capture differences in groups, gives better estimates, but for small size groups, but doesn't use the predictor variables. It's only using the intercept. Hierarchical models provide the answer here. They use all the available information in the data, including the predictor variables, to provide better group target or response values, so better predictions, even in small groups. So they do an excellent job of combining the data that we have to give us good results. Okay, let's look at how this might work on a particular case, which is known as the radon testing example. This problem comes from the book by Gilman and Hill, Bayesian Data Analysis, published in 2006. So radon is a radioactive gas that enters homes through contact points of the ground. The bad thing about it is it's a carcinogen, and in fact, it's the primary cause of lung cancer in non-smokers. There are varying levels between houses, and the question is, when you go out and do the testing, can we model the conditions that would predict those different levels? And fortunately, the EPA has measured this in about 80,000 homes. We'd like to have more data, but at least we've got 80,000. And we're just going to look in the example that we're going to look at for this lecture just at Minnesota, just at the state of Minnesota. It provides an interesting example of how to use hierarchical models. So there are two important predictors that we can think about. The floor, basement or first floor, and the county and the uranium levels. In the code we're going to show you, we're just going to use the basement or first floor levels, and you can look at additional results that have been published that show how to use the uranium levels as well. It's an interesting problem. So let's look now at the code. So as we mentioned, this example comes from the book by Gilman and Hill, printed in 2006. And there's the link to the code that we're describing here, and additional code so you can do additional things with this particular data set. It's a pretty rich data set. So the first part of this code just does the typical things we do. We're loading packages, we're loading the data, we're taking the Minnesota part of the data out, so we're not looking at all states, just Minnesota. Then we're doing some cleaning on the variables. And we see that we have a summary of the data, or we have the head of the data displayed to give you a sense of the number of variables that are here. 27 columns in the data set. Here's a histogram of the radon levels in the counties of Minnesota, and you can see that there are definitely quite a few counties above zero, and the mode in this particular histogram looks like it's about 1.6. So the complete pooling model is represented by the code in this cell, and you can see that we have a simple regression model with a intercept term, beta naught, and a slope term, beta 1. And the predictor, the single predictor, is floor, which can be 0 or 1, representing the basement of the first floor. In the graphical model as shown, we have two beta parameters, both with Gaussian prior distributions. The standard deviation on the regression model has a half Cauchy distribution, and there are 919 observations in the problem. So we run the Hamiltonian Monte Carlo for this problem with 4 chains for 4 processors or 4 cores, and we get the results shown, which look pretty good for the two beta values. Both of them look like they've converged. And the same is true for the sigma, although the density plot for one of the sigma chains looks a little flat, close to its maximum, but its performance in terms of its convergence looks pretty good. Now, look at the plot for the pooled model. This is why we don't like this model, particularly for this problem, because it's a pretty ridiculous plot. You can see that the regression line here is pretty much telling us almost nothing in terms of the performance. We have no real idea how these counties behave in terms of their radon levels. So it's really giving us no information at all. So the pooled model in this particular case is pretty much a worthless approach. So let's now look at the unpooled model. And recall in the unpooled model case, we build a regression model for every county in the state of Minnesota. So in this case, we're going to build one with a intercept term that depends upon the county. And the graphical display of the model is shown here with 85 beta knots for each one of the counties. We're going to keep the beta 1 based upon the pooled model, and sigma, again, is going to be a half Cauchy. So the betas are going to have priors of Gaussians, and the sigma will have a half Cauchy. The results of this particular model are shown here. We can see the, again, this is running our Hamiltonian Monte Carlo to get the results for each one of the parameters. In this case, we're just showing the parameters, the intercept terms, and we're showing the confidence intervals or the credible intervals for those each one of those intercepts. Another way to see this is to plot the results in terms of the radon estimates, and you can see how the radon estimates vary widely across the different counties based upon this model. And finally, most dramatically, we can take a look at the counties with the least number of observations. The population size is small. They have a small number of observations, and the ones with a large number. And the ones with the small are shown in the top row in these figures. And you can see that the county on the top left, the Lac Qui Parle County, only has 2 observations. So the regression that we get is quite different from the dotted line representing the unpooled model. So that's for all the counties. And you can see there's quite a difference. But the question is, with such a small sample, do we really trust the regression that we're getting there? And in each one of these cases, for these counties with small numbers, you can see there's a difference between it and the overall average. But the question is, how trustworthy are the predictions based upon these small numbers? On the other hand, you can look at the ones on the bottom, and you can see that the results for the larger populated counties are closer to the overall average, with the exception of St. Louis, which is a little bit far, but it's because the variance for the basement and floor results is quite dramatic. But by and large, it's closer for the larger counties to the overall results. Okay, but we really don't trust these results from this unpooled model because of the fact that we have counties with small numbers and counties with large numbers, and there's quite distinct results there between the two. So let's next look at the partial pooling results. Recall for partial pooling, we have a model that does not have predictor variables. In this case, the one predictor variable. It's dependent only on the intercept term. And you can see in this case, the model we have for the intercept uses a Gaussian to represent the model itself. Again, the half Cauchy to represent the variance associated with that parameter, and then a half Cauchy again to represent the variance associated with the model. The model results are here, and you can see what we've done is on the left we've plotted the unpooled case, and on the x-axis we have the population size of the counties, and on the y-axis we have the prediction of radon. And you can see that the one on the left is the unpooled case, and the one on the right is the partial pooling result. And you can see this, why we call this shrinkage, that these results are pulled closer to the overall average for the totally pooled case, which is represented by the dotted line running through the middle. And the interesting thing is for the counties that are very small, and they're on the far left of both of those two plots, the results are quite striking. There's one county there that doesn't even have enough observations. and we saw that earlier. It's got 2 observations. It doesn't have enough to give you a confidence or a credible interval, but that's pulled much closer to the overall average prediction because it is such an extreme case that the extremity of its results are not believable for the entire county. And you can see that that same is true for all the results that are pretty much at the low end, that they're pulled much closer to the average. Whereas the larger counties don't move quite as much in terms of their movement in the direction of the overall average. Again, that's called shrinkage. Okay, so let's next look at the hierarchical model. So for the full hierarchical model, we have Gaussians for the prior distributions for each of the beta parameters, and we also have distributions, half Cauchys, for the variance of those 2 parameters. We have a we have a uniform representing the prior distribution for the variance of the model, and the results now we get are for both betas. We have credible intervals for both betas, which are shown here. But most importantly, we have the results shown in the last cell of this Jupyter Notebook. And now you see that we get to the advantage of the hierarchical model. So we actually have good predictions for each one of the counties in Minnesota on their radon. Instead of having the really worthless prediction we had for the totally pooled data, or the questionable predictions that we had with the unpooled model, and the okay predictions, but unfortunately without a predictor variable for the partial pooled model. Now we're using that predictor variable along with the intercept term, and we can see that for each one of the counties we get a prediction of what its radon will be. And we're a little bit more, I shouldn't say a little bit, we're quite a bit more trusting in these results, because what we've used is we've used the data from all points to help represent what might be happening in those counties with very few data points. So it's as if we're imputing the missing data that we have in those counties to derive better estimates of what their predictions might be. So this is a nice little example to show you how hierarchical modeling works and how it's important for a large class of problems in the real world.